So it will be a talk in a different style than what you've seen. There's no PDEs, no theorems. I used to be a mathematician actually, but now I'm an ecologist, so I don't really try to go for theorems, but I use mathematics a bit as a sophisticated metaphors to, let's say, expand the way of thinking that we have on ecological systems and potentially generate interesting hypotheses. Right. Okay. So the context in general, the stuff I'm interested in is ecological communities. So by that I mean like different population, different species that have interactions with one another. So this is a classic example from a paper by Pocock et al. Where they try to map out the network of interactions in a terrestrial ecosystem. And I don't want you to focus on details there at all, but just to understand it's complicated. There's a lot of various interactions. And the consequences of those interactions is something that is of interest to me. And yeah, what kind of collective process patterns can emerge from interactions. They're not necessarily built into the population dynamics of individual species or the environment, but it's taken together that some patterns emerge. So that's the kind of questions I have in mind. At this point, it's vague, but something a little bit more precise, just to introduce my motivation. It would be the possibility that you'd have a community composition transitions along a smooth environmental gradient. So abrupt transition of community composition along a gradient, when you could follow some gradient of altitude, of salinity, of temperature, whatever, and you would observe the ecological system, and at some point, abruptly, let's say, in a certain sense, it transforms into a completely different community. And of course, you could imagine various processes that could lead to this. And again, the kind of things I'm interested in is the possibility that it is through the interactions between the various species that this occurs. So that's the thing of interest, let's say. But as often in ecology, the thing of interest is hard to access. And the object of study, if you will, is a mathematical object. And the kind of mathematical object that I'm going to talk about is the same kind that Ada described and Elisa also. So it's this classic model. Let's say the theory I've thought about is slightly more general, but it's this idea that you describe the growth rate of populations. So the size of the population would be n, and I index the species. And so the Ri would be the growth rate. And so this encodes some basic ingredients of what we think about when we think about nature, is that there's some intrinsic exponential growth of populations. That's one thing. And then there are those interactions that I talked about. So it's this matrix A encodes interactions, intraspecific interactions, like intraspecific competition typically, but also interspecific. And in this form, this is the simplest possible form where those interactions are linear. But of course, people have argued that it's not linear, it's something else, but that doesn't really matter. This is really the baseline. And something that such models do is allow you to study processes of assembly, like Ada described, for instance, where you'd have like certain species in a pool and they assemble, some go extinct, and some survive, and then if you vary conditions that would be encoded into the intrinsic growth rate, for instance, you could see invasions and extinctions occurring. Right. So the reason why I started the work about those abrupt transition is because there was a PhD student where I worked that was studying precisely that in simulations. So he was simulating the kind of model that I showed, where the interactions were competitive, and depending on the strength of interactions. So in the middle here, you go from no interactions at the top to a strong interaction at the bottom. and the curves denote the abundances of different species. So, and on the x-axis, it's a spatial or environmental gradient. It's the same for in his work. And so when there are no interactions, in the top panel, you see smooth transitions. Some species are more abundant where the environment is the most favorable to them, and as you move away from it, they decline and so forth. So you have this turnover that is continuous. And at intermediate interaction strengths, that's where you have these transitions, abrupt transition between various community compositions. So you have some smooth variations within one cluster, and then at some point, something discontinuous occurs. You have a different community that pops up. And what he found, I mean, studying numerically, is that this has to do with the occurrence of alternative stable states in the system, where for a given environmental condition, let's say, for instance, if you look at, so when there are no interactions, there are no alternative stable states. But here, for instance, you see that for a given environmental condition, there could be two, or maybe even here you imagine maybe there could be three. Here, three possible states, for instance. So those abrupt transition, alternative stable state, they seem to go together. And that's something I wanted to understand a bit better. I mean, a bit more analytically, let's say. And what I quickly realized looking at this is that those transitions, they are triggered by either invasion, so a species that was not present is now able to invade, and due to its invasion, it's causing something, or an extinction. And so, to understand why they can be abrupt transition, let's dial down the complexity and think of just two species, and think of the kind of scenarios of invasion of one species invading a resident, what kind of scenarios you could have, at least for these simple models. So the important object here is the growth rate when rare, or the invasion fitness. So it's the intrinsic growth rate that is maybe reduced by the competitive effect of the resident. And you can look at if you write down the coexistence equilibrium, so the equilibrium of this newcomer that in the talk, the index 0 is here to represent the invader. And you could look at what's the abundance of the invader, at what abundance does it settle in. And you see that it's proportional to its invasion fitness. And this proportionality, you can see it here by the fact that when I, on the x-axis, show a gradient of invasion fitness. So if the invasion fitness is negative, well, the invader the abundance is 0, it cannot invade. But as soon as its fitness is positive, it can invade. And in some cases, if the conditions get better and better, well, its abundance grows. And in this first scenario, the abundance grows. But as you can see, it will never reach the abundance that it would have had if it had been alone. So in green, this is the abundance that it would have had if there were no resident, if it had been really on its own in the environment. And on the right, you see that maybe the slope of the red curve is steep enough that if conditions are good enough, it will reach the abundance it would have had if it had been alone. And you can guess that this means that at this point, it has pushed the resident to extinction. And the slope can be steeper, it can be vertical, so that's very particular, and in which case as soon as you can invade, you immediately replace, but it can be even negative. And what you can show by doing a little stability analysis is that it means that the stable coexistence is, the coexistence is unstable. And this means here that you have you have mutual exclusion, basically, because as long as the invasion fitness is negative, it cannot invade, but as soon as it can invade, it jumps to its abundance if it had been alone, pushing the resident to extinction. But if you reversed the conditions back, it would not go extinct at the conditions where its invasion fitness had been 0. You have to go further until then it drops back to 0. So you have hysteresis typically. And you have, in this zone here, you have mutual exclusion between the resident, so that's when the invader is 0, that means the resident is alone, and the invader is alone, the resident is extinct. Okay, and this slope is given by the inverse of this thing. And I wrote it like this because, for a reason that will become apparent later, is because I want to call this, I want to call F feedback, something that has to do with feedbacks. All right, and what you see is that if the sign of this value that has to do with the interactions between resident and invader, this decides if there can be abrupt turnover or not. So let's try to think about the more general argument that you could make that will hold in more complex communities. So you'd start from the invasion fitness. So the growth rate when rare, and what we're going to do is that you're going to think about the growth rate of the species in a bit of an abstract way, where you have to imagine that the growth rate, if you could measure it by fixing the abundance of that invading species and letting all the rest settle, and then giving you the value of this growth rate. So now the growth rate, in this abstract sense, becomes an explicit function of the abundance of the invader. All right, and so its value at 0, its intercept at 0 is the invasion when rare, the invasion fitness. But if you go a little bit beyond rarity, you can do just a linear expansion, and you have the total derivative. That's important, the total derivative. And by total, I mean that it will have to do with everything else that is in there in the system, maybe many other species. And its total derivative is what I want to call the feedback. It's how the growth rate is affected by the abundance of the invader. So it's a density dependence effect. And so just by saying that the invasion end when the growth rate is 0, if you solve this equals 0, as long as this linearity holds, you get the expression I had before, that the abundance is proportional to the fitness and divided by the feedback. And so if the invasion feedback is positive, it means that the more abundance of the invader there is, the more growth rate there is. And so there is a runaway process that means that this linearity assumption cannot hold. Something drastically nonlinear is going to occur for the growth rate to decay and the invasion to stop. And so that means that there will be some transition at whenever the growth rate crosses the 0 threshold, the invasion threshold. And so here's an example on a simulation. So on the left, you have the community, and what I'm varying on the x-axis is some environmental conditions that is favoring this invader and not really affecting the other species. So as long as the invasion fitness is 0, nothing is happening. But at the red star, the invasion fitness becomes positive. The invader can invade, and because its feedback is positive, it causes some abrupt shift. There is some species that are going to extinctions. You can kind of see it behind there. This blue one is going to extinction, and you have this reorganization. All right. So if I go back to my two species case, what have we done? We basically looked at the graph of the growth rate function, large R, as a function of n naught, and we basically just said, well, we have the intercept, that's the fitness, and we have the slope, which is the feedback. And sometimes when the slope is very negative, it means that you quickly reach a 0, where at this point the invasion ends. But if the slope is not steep enough, then maybe you're going to push some resident species to extinction. And if the slope is positive, then you're definitely going to push some species to extinction. And after that, you're just following your own intraspecific density dependence. And this is the case where there's alternative stable states where the invasion fitness is negative, but the feedback is positive, which means that if you could start the invasion at a large enough abundance, then you would have a runaway process that would lead to the extinction of the resident. Right, and you can graph these various scenarios in a phase space where you have feedback on the x-axis and fitness on the y-axis, and that is for two species. And you have the different scenarios in there where you have some coexistence where, so in red that means that the invasion has failed, the fitness is negative, and only in this alternative, in mutual exclusion or alternative stable state zone, here it means that the success of the invasion depends on how of the initial density, and then up there there's turnover, so replacement of the resident. And what's nice about that is that you can extend, because we saw that the notion of invasion fitness and feedback was something we could generalize to more complex systems. And so this graph, this phase space, you can draw it for more complex communities. So here, this is large random Lotka-Volterra communities where we generated the communities, and then we generated some invaders and looked at what was happening. And the colors are used by an algorithm that is trying to decide where to put the line, and it looks very much like the two species case. And if you worked it a bit more carefully analytically, you could find that under a certain rescaling of the axis, then there is some universality, a way to universally draw this phase space. And you see on the little inset here that the different scenarios have relate to different impacts on the community. And here I'm looking at the fraction of extinctions in the resident communities. And so when the feedback is large and the invasion fitness is large, that's where you'll see a lot of extinctions in the resident community. So this is something we try to do, is trying to predict the impact that it will have on the community based on invasion fitness and invasion feedback. So the initial slope, intercept and slope. And basically what we try to quantify, and I know I'm being very hand-wavy here, I realize that. I'm just trying to give you some slight intuitions, but what you see is that you want to measure somehow the tendency for this growth curve. So this is what it would be doing if it had no effect on the community. In blue, it would be doing if it was on its own. So it had wiped out everyone. And you want to say something about how the tendency that the system is in getting close to this extreme case where it has wiped out everybody. And so that way you can work out geometrically some estimator of impact and predict the effect. And so here are some results. So here we try to predict the impact just based on invasion fitness, which is a bit the empirical classic way to do is say, oh, how good are the conditions for this invader originally, and is that predicting the overall effect it will have in the community that invades? And you see here some correlation, but it's not amazing, especially given that we are in an idealized mathematical setting. We don't want to be too happy with a cloud of points like that. And so if you put in there the notion, the knowledge of feedback, well, you get something better. It's definitely not perfect, and we know it cannot be perfect because it's really only using information about the initial tendencies of the invasion. It's not really seeing what's going on much further. But at least here we see something better, and we see that we organize the colors correspond to the different scenarios. So blue is coexistence, and black and green would be like turnover regimes. And we see that we are organizing those colors quite well, where it's in turnover that there is more impact. Here, impact is measured in terms of the relative change of abundances of resident species. So, but what is this feedback concretely? Can we have some intuition of what it is? And what I want to explain to you is that it has something to do with interaction loops and stability, or sensitivity to perturbations. And the intuition is that you have an invader. Its presence is perturbing some resident species. This perturbation of the resident species is perturbing others, and the other species is having an effect on the invader. It's this loop that is determining the feedback. And if you want to do it a bit more formally, you say, okay, you do a little shift in abundance of the invader. This will shift have an effect on the abundance of the species, which will feed back on the growth rate of the invader. And this, so basically this term is the perturbation that the presence of the invader is having on species J. And the matrix Vij is the matrix that encodes the net effects that species J is having on species I. And what's nice about that is that, at least in Lotka-Volterra models, but in general you can generalize it a bit, is that this matrix V is determined by the matrix of direct interaction, but it's just the inverse. It's the inverse matrix. And if you write it down, then you get this expression, which, okay, that's the mathematical expression, but the intuition behind this expression is that you're summing over all the interaction loops that go from the invader back to the invader, and you're summing all those loops. And this matrix V, which is it tells you how sensitive the abundance of one species is to a change of growth rate of another. So it's encoding the sensitivity of the community to perturbations. In physics term, this is really the notion of linear response or sensitivity. So it's connecting those two notions. So I should speed up a bit. But something I wanted to talk about real quick is that this also, I don't know if some of you know much about linear algebra, but if you look closely at what this expression is, it looks like a block inversion. So you're trying to do a matrix and you want to do a block inversion, and this term, this feedback, is exactly the kind of expression you would have when you do a block inversion of a matrix. And I'm just mentioning this because this calculation of feedback, I could be doing it not just for invaded, I could be also doing it for residents. And this notion is going to enable me to connect to a notion, to what happens when there are extinctions. So suppose you have a community and you look at a given resident species, and let's say that somehow the total derivative of the growth rate, which has to do with the inverse of the interaction matrix, somehow is the feedback is positive. This seems contradictory to the assumption that I'm looking at a steady state, because it implies that if there had been such a resident species, in the moment where it was invading the community, it would have been what I call a hard invader, an invader that has positive feedback. And so it would not have been able to coexist with the rest of the community. But I see it coexist with the rest of the community. So either this situation cannot exist, or if it does exist, it means something else entirely. It means that it's the rest of the community that cannot exist without this species. So it means that when this occurs, as a species that experiences positive feedback is a keystone species, its extinction will cause an abrupt transition, an abrupt reorganization of the community. And I thought that this was not occurring in those models, but it turned out that it did, because I told, a student he was getting back at me saying that he was finding those cases now, and I kept telling him he was making mistakes. And in fact, no, he was actually right. And here's an example of this occurring. And this one, it's a bit of a involved example, but I thought, and I found it a bit like cherry picking some simulations. It's not necessarily a generic outcome, but let's see what's happening here. What's interesting here is that I'm varying some environmental gradients, and originally here there are no keystone species. There are no species that are seeing positive feedback. But this black dot, there's a species that invades. It's a soft invader. It means that when it's invading, it's settling at some abundance, but it's not causing abrupt organization. But what it's doing is that it's making the red dotted species, it's making it a keystone species. And as the environmental gradient goes, this keystone species abundances decays. And at the moment where it goes extinct, boom, you see this abrupt transition. This is just an example that these things can occur. All right, so let's try to summarize briefly. And then after that, I would like to move on to some more perspective work about evolution, where I'm way less confident. So, yeah, you might hate what I will say because it will be wrong, but that's okay. But so what we did so far is provide a local analysis of the growth rate function defined in a certain way. And we showed it provides some extension of classic invasion analysis that connects the role of fitness, feedback, and indirect interactions in the communities to assembly patterns, some assembly patterns. Oh no. All right, I'll finish the talk, please. And that sharp transitions that I was interested in to begin with, they require either a hard invader or a keystone resident. But each time, it has something to do with there being positive interaction feedback loops in the community. And so the idea that that positive feedback loops have something to do with alternative stable state is well known, of course. But here the contribution is to precisely write down what those feedback loops are, what are concretely where they're coming from. Okay, so in a few minutes, I want to say something about some perspective work, where so far I talked about invasion as some exotic species, some species coming from outside and invading. But you can imagine that this invasion is coming from within, so from a mutation, let's say. So so this is my attempt to see how can I connect with some ideas of evolutionary theory. And in particular, trying to address this idea that the environment, here represented by the whole community, is very dynamic. All right. So this is the internship of a student at the moment from his master is called Darwin, so it seemed suited to do that. And so now the invader is a mutant, and the way I'm going to formalize this is just by saying the dynamical characteristics of this species is just shifted from the one of a resident by some epsilon-esque terms. And so if I calculate the invasion growth rate, this is what is classically known as the fitness, is going to be of the order of epsilon. And the feedback is going to be also of the order of epsilon, but only if the mutant ancestor are different, possibly different from the ancestor interactions. And this is, sometimes this is makes sense, sometimes not, I'm not sure. Otherwise, it will be of order epsilon squared. And that's, from what I understand, this is a more usual setup for adaptive dynamics. I'll explain that in a second. But anyway, the point is that if you take epsilon to go to 0, so the effect of mutation will be really small, invasion here becomes really, regardless of how complex the community, it really becomes a two-body problem. It's really a question, something that the resident and the mutant have to work out together. And the rest of the community is acting a bit like the scene, the fixed scene in which this play is taking out. But the kind of question I'm interested in is how small this epsilon should be for this to be the case, for this to be just a two-body problem, for the community to not start to really dynamically interfere with the fixation process. So this is the ancestor mutant phase space, where based on the theory I talked about before, you could have like fitness feedback, and you have the different possibilities here where you have maybe replacement, so total fixation, coexistence, some maybe density dependent. And as I said, the classical adaptive dynamics, because of as I said, the feedback was order epsilon squared, it's taking place on the vertical line. But in general, not necessarily. And what we did is to try to show that due to the complexity of the community, if epsilon is not absolutely 0, the dynamical nature of the environment, the community, can create qualitative mismatch, can push away from this two-body problem. So the points that I'm showing here are those points that should not be the color that they are based on the two-body problem. It means that there, for instance, you have failed invasions that shouldn't have failed based on if you had just worked it out from the two species case, but they have failed because of the community, and so on. So just, oops, sorry. My point here is that the community is participating in the selection process, like beyond just saying what the invasion fitness is. And so the selection environment become inherently intertwined here. And that may not be the perfect way of saying this. Like if you have a better way of viewing it, I'd be very happy to discuss this. Right. And this is my last slide. And here was that the qualitative mismatch. But if I look at quantitative, so if I look at what do I expect the abundance of the population that has mutated after the mutation, based on just looking at the two-body resident, ancestor mutant problem. So if the interactions within the communities are small, on the top left, you see that basically the two-body is predicting things very well. But as the community, the interaction within the community become larger and larger, it becomes less and less the case. At some point, it becomes a bit messy. And what's interesting is that as it becomes messy, it's also because you start to appear these orange dots that show that there are some keystone residents. You remember those keystone species within the community that experience a positive feedback. And yes, so this is just some vague observation to show that that when interactions between the species are strong, the environment represented by the community with respect to the population that is mutating is having a dynamical impact on the invasion process. Okay, so some quick questions for you that what does that say anything about our understanding of coevolution? I have no answers to these questions, of course. Maybe this is utterly negligible, it doesn't really occur. And of course, many of you have explained, there's a lot of interesting subtleties when you consider finite populations, so stochastic dynamics and like spatial dynamics and so on. So yes, thank you very much. Sorry, I'm a bit late.
Thank you very much. Are there questions?
Thank you very much. Did you answer the question how epsilon can be chosen small enough?
No, I don't have the precise answer. I thought the answer would be easy because I thought, well, it has to do with the sensitivity of the community. So if I can have a metric of the sensitivity, well, it will be the inverse of that, let's say. But I don't know. I haven't converged on a precise statement, but it has to do with that, So the more unstable, the more if the community is close to being unstable, so it's like in a critical state, then a small perturbation represented by the invader is going to have big effects. So that's the intuition there. That I would like to make that statement more precise, but so far I haven't. I haven't reached the right formulation.
Do you have an estimate of how many alternative stable state do you have in the phase diagram concerning the first part?
Right. Yeah, I wanted to talk a bit about that. Yeah. So the kind of you meant in the work of Kevin, where I showed alternative stable states in the community
at the very beginning.
Yeah. So it's not a lot. It's not the regime that you consider of many species where there would be exponentially many alternative states. It's a bit of an in-between regime where it's not it's strong interaction and not so many species, and so I don't know how. It's hard to give a precise answer, because if you go to very large communities like you do, you don't get those kind of very distinct alternative states. You get the kind of stuff you showed. So For sure, the things I looked at were, there was no general rule that I could say. It was not huge amount of species, so it's a bit idiosyncratic, if you will.
Like, can I ask another question? So I will add another question about the second part. So the influence of this keystone can be somehow related to a sort of Ali effect that you show in the phase diagram, in the bottom part of your phase diagram.
Is it related?
Yeah, this is the question. Is it related or not? The fact that you don't have just, let's say, a two-body problem, that you should take also multi-body problem into account and cooperative effect.
When they are in a case where you're talking about evolution.
In the second part of the talk.
I don't know. You mean that maybe a mutation is causing a jump to an alternative stable state, for instance?
No, I just mean when you show the influence of the keystones, so the orange dot.
Yeah.
Yes, on the third plot. So you said at a certain point that, okay, maybe this two-body problem is not exact, so you have other effects. So it can be somehow related to the bottom part of your previous phase diagram when you have this Ali effect.
Yeah, I think here the Ali effect is really between, it's something that it's mutual exclusion of the mutant and ancestor.
Okay.
Whether the keystone is something that have to do with the rest of the community, so it's not really present in the two-body problem. I think it's just that at some point this phase diagram just breaks down completely.
Okay.
It's making no predictions.
Okay.
Yeah.
Thanks.
Okay, thank you. Maybe in the interest of very last.
Again, about the keystone species, is it possible to do it with three species only?
Sorry?
The keystone species, is it possible to have it with only three species only, or why? Because at some point you say it was not generic, or at least it was not expected. Is it possible to resolve the free body problem to?
Yes, I think it requires at least three species in community to get that. Yes. So by not generic, I mean that if you just generate randomly your communities, you're not going to find them super often. So it was a vague statement, but yes, as long as I think it's 3 is the minimum.
Thank you very much.